Hello, future engineers. Welcome to my YouTube channel. To keep me going, please share my videos to your friends. And to those who are new in my channel, please also share to your friends so that that's the only way that you can energize me, you can inspire me so that I will do more lecture and sample problem videos beneficial to you and to my future subscribers. So here we go. This is the last problem, and this is a very challenging one. It may not come out in your um, quiz or exams, but if you can follow the explanation and solution to this problem, you will be more than prepared, and that will be your ticket to say that you have understood the principles on deflection by the area moment method, and that can help you boost your skills as an engineering student, or maybe you're an instructor or professor of your field, chosen field, especially in civil engineering. So here is the problem. We have two hinges here. So we plan to select, because there are two hinges, then there will be three moment centers if you do not select these hinges. So we select A, I select A, C, and E as moment centers for this problem. So because for portion AB, it is readily can be easily analyzed. The 30 kilonewton load, concentrated load, is acting at the center. So naturally, if you sum up moment about B, considering AB, the reaction here would be 15. Similarly, at B to the left, it's also 15. Then by action reaction at the hinge, so we have 15 down. Then we consider next this portion. We sum up moment about D vertical, about C rather, equals 0. So moment about D equals 0 to solve for R sub C. Supposedly we will not solve for R sub C, but anyway, this is the setup equation. So R sub C, assuming upward, times, so clockwise moment positive, RC times 4 plus 90, then minus 15 times 7, then minus 20 times 3, then 1.5 plus 4 is 5.5. So minus 20 times 4, times 3 rather, times 5.5. So solving for the reaction at C. Reaction at C is equal to 86.25 kilonewtons as shown. Then summation forces Y in this portion equals 0. So negative 15 minus 20 times 3 plus R sub C, which is 86.25, assuming vertical reaction at D to the left, just to the left of D sub V, then D sub V is equal to negative 11.25 kilonewtons. So meaning to say the reaction at D just to the left is downward as shown. So by action reaction, just to the right, it should be 11.25 kilonewtons also. So finally, for portion DEF, let's solve for RF. Summation moment about E equals 0. Then assuming RF is upward, so RF times 6, so counterclockwise moment positive. Then 11.25 times 5 is clockwise, so minus. Then 15 times 11, so center is 5.5 on the right, and this is 6, so means 8.5, and it is also clockwise, so minus. So minus 11.25 times 5, then minus 15 times 11 times 0.5. Solving for RF, RF is equal to 23.125 kilonewtons as shown. So we are now ready to construct the moment diagram by parts. Remember, we select A, C, and E as our moment centers. So beginning with this part, 30 times 2 is 60 over EI. Then 15 times 4 is also 60 over EI. So that checks because the moment at A is 0. Then to C, so we begin with 15 times 3 over EI, so 45 over EI. Then due to this load, second degree, 20 times 3 times 1.5. Then second degree, 20 times 3 times 1.5 is 90 over EI. Then this 90 kilonewton is rectangular below 90 over EI. Then due to 11.25, triangular 11.25 times 4. 11.25 times 4 is 45 over EI. Then to E, 11.25 times 5 divided by 2. That would be divided by 2 because the moment of inertia portion DEF is 2. 28.125. Then due to this loading, 15 times 5 times 2.5 second degree, then divided by 2. Again, 15 times 5 times 2.5 divided by 2. This is second degree curve, and the moment here over EI is 93.75 over EI. Then for this loading here, 15 times 6 times 3 divided by 2. 23.125 times 6 divided by 2 for this reaction is 69.375. Then for this loading, second degree, 15 times 6 times 3 divided by 2. Second degree, and this value here is 135 over EI. So this is the complete moment over EI diagram. So for the analysis, we begin with DEF first, then we want to know the slope of the tangent at E, so that we will transmit it here, then compute for deviations just to the right of D, so that we can analyze the deflection as well as the slope, and as well as theta DE, D right E, and so on and so forth. Then we proceed to portions BCD. We need the slope again at C, so that we transmit it to D to the left, so that we can analyze the slope at D to the left, as well as the deflection at B, which is only required at B. So first, EI deviation of F relative to E, so that we can solve the slope at E. So considering the areas, moment of areas between E and F, there are only two areas. Then with respect to F, so for this positive area, 1/2 or 0.5 times 6, then the centroid 2/3 of 6 is 4 from F rather. Then minus 1/3 area times 6 times 135. This distance is 6 divided by second degree plus 2, so 6 over 4, 1.5. So the distance from F is 4.5. So minus 1/3 of 6 times 135 times 4.5. So this is equal to negative 382.5 over EI. So that means that that point F is below the reference tangent at E. So we draw the tangent at E. Then this is the meaning that deviation of F relative to the tangent at E is negative, and so F is below the reference tangent as shown. So this is the slope of the tangent at E, which makes with the horizontal, and therefore it is positive because it is inclined up to the right. So this is equal to tangent of theta E, or theta E itself, this deviation divided by 6. So that's theta E. This is also theta E. So theta E is 382.5 over 6 EI because theta E is positive. So theta E is 63.75 over EI. Next, we compute for the deviation of D relative to the tangent at E this time. So considering this area is 0.5 of 5 times 28.125 times moment arm from D right, the first letter here is 2/3 of 5. So this is D right, 2/3 of 5 is 10/3, then minus 1/3 of 5 times 93.75. This distance is 5 over 4, 5 over second degree plus 2, 1.25. So the distance from the right is 3.75. The moment arm is 3.75. So minus 1/3 of 5 times 93.75 times 3.75, distance of centroid of this area from D right. So computing deviation of D right with respect to E is negative 5625 over 16. D right is also D to the right. This symbol here is the same as D right. Then D negative, or theta D negative, is the slope at D just to the left, or D left. So meaning that D, this point here, is below the reference tangent at E. So this hinge will be exaggeratedly here. Let's put it here. And this is the deviation of D right with respect to E. Since this distance is equal to 5 times theta E, because we have a right triangle and we already know theta E, so this is 5 times theta E. And we can compute now the deflection at D. It is negative of absolute value 5 theta E plus absolute value of deviation of D right with respect to E. But before that, let's solve first the slope at D just to the right by computing theta D right E. So EI theta D right E is simply the area between D and E. So we copy these terms except the moment arms. So 0.5 times 5 times 28.125 minus 1/3 of 5 times 93.75. So theta DRE is equal to negative 1375 over 16 EI. So that means because that's negative from the tangent at D right to the tangent at E, it is clockwise. So the tangent will be above the tangent at E as shown in the figure. And this angle here is theta DRE. And this angle here is theta E. The total angle here, this is the tangent at D right to the horizontal, is theta D right. Therefore, it is inclined up to the right. This is also theta D right, this one from the horizontal. So this is also theta D right. Therefore, theta D right is positive of absolute value of theta DRE plus theta E, which are already known. So theta d right is equal to positive of absolute value of theta d right E, which is negative 1375 over 16 EI plus uh, theta E, which is 63.75. So solving for theta d right, it is equal to 149.6875 in decimal form. So next we have to solve for the deflection. So delta D is negative of absolute value 5 theta E plus absolute value of deviation of dr with respect to E. So 5 times this is theta E, 63.75 plus the absolute value of deviation of D right with relative to E, which is this one. So adding, and the sign is negative in decimal, is equal to negative 670.3125. So it's the same answer as in double integration. Finally, we proceed to this part. Let's solve for deviation of D left relative to C. So EI division of D left relative to C is moment of area between C and D left, these two areas here, with respect to D left. So these two areas are negative, so 2 meters by negative 2 meters times 90, the distance of the centroid from D left is 3. 1 plus 2, so 3. And for this triangle here, minus 0.5 of 4 times 45. The moment arm is 2/3 of 4. 2/3 of 4. This distance of centroid to D left is 8/3. So computing, deviation of D left relative to C is equal to negative 780 over EI. Negative means this point hinge here, D left, is below the reference tangent at E. And because this is negative 780, which is greater than delta D, delta D is only 670, in magnitude this is 780. So that means that the tangent at C is above D left, so that the vertical distance, which is negative, because this is below the reference tangent at C, is greater than delta D. Delta D is only 670, while division of D left relative to C is 780. So as shown in the figure, so this is division of D left relative to C, so that theta C is positive, it is inclined up to the right, and it is equal to this value divided by 4. This value is equal to this total value minus deflection at C. So this is theta C. So EI theta C D left is simply area between the two. So we copy the area except the moment arm. So negative 2 times 90 and negative 0.5 times 4 times 45. So theta C D left is negative 270 over EI. What does that mean? That from the tangent at C to the tangent at D left, the rotation is clockwise, as shown. So this angle from the tangent at C to the tangent at D left is theta C D left, that one. And because the angle that the tangent at C makes with the horizontal is theta C, the angle that this tangent makes with the horizontal is theta D left. This is theta D left from the horizontal to this tangent here. So therefore, it is inclined down to the right. It is a negative slope. So theta d left is negative of absolute value of theta c d e left minus theta c. So that is theta c is positive of this total vertical distance, absolute value of division of d left relative to c, minus delta d, which is this one, over 4. Again, the slope at c is this vertical distance. This vertical distance is positive of absolute value of this minus delta d. So that is left. So absolute value of 780 over EI minus delta D. Absolute value of delta D negative 670.3125 over EI all over 4. Remember, tangent theta C is theta itself. Theta C itself opposite over adjacent. So theta C is equal to 1755 over 64 EI. Then we can now compute theta D left. As I said, it is negative, sloping down, of absolute value of theta C D left minus theta C. So theta D left is negative of absolute value of theta C D left, which is negative 270 over EI, minus theta C. Theta C is 1755 over 64 EI. So theta D left, or theta D minus, is negative 242.578 over EI. So finally, for deflection at D, since we already know this, we compute for deviation of B relative to the tangent at C. So it is the moment of area between B and C. There are two areas with respect to B. So for this triangle, negative area, so negative 1/2, negative 0.5, times 3 meters times 45. Then the centroid is here, 2/3 of 3 is 2. So the distance of the centroid from B is 2. Then this is negative area again, minus second degree, 1/3 of 3 times 90. The distance here is 3 over 4, 0.75. So its distance from B is 3 minus 0.75, so 2.25. So minus 1/3 of 3 times 90 times 2.25. So solving for that deviation of B relative to C, it is negative 337.5 over EI. What does it mean? B is below the reference tangent at D left. So this is the position, and this is deviation of B relative to C, and this distance is 3 times, because that's 3. This is theta C, so 3 theta C. So we can now analyze the deflection at B. It is negative of absolute value of 3 theta C plus absolute value of deviation of B relative to C, but it is negative. So delta B is negative of absolute value of 3 times theta C. This is theta C, 1755 over 64 EI, plus absolute value of deviation of B relative to C, negative 337.5 over EI. So delta B in decimal is equal to negative 419.766 over EI. So that's it. If you're able to follow the solution, it's an exerted effort for you to follow and understand, and the applications, the explanation will be based on the principles as well as the geometric meaning as shown in the figure. Although crowded, but you can see it because of the pointer. I hope that the narrations and the the animations coordinate well.